Okay, a major problem that's going to come up with what we're doing today involves another kind of improper integral. How many have had statistics, Math 119? Okay, there's something called the normal distribution. Yes. And it's this. If I draw the graph, and by the way, this is actually be the z-score. It's right x minus mu divided by sigma. But we do this. The graph of this looks like this. This is when people refer to the bell-shaped curve. That is the. There's not versions of this. That is the bell-shaped curve. And what happens is if you have a normal distribution, that means you're going to have symmetry. That means we know the population mean, standard deviation, all these things. But I need the area under this curve because let's just say hypothetically the area under this curve was 5. Then what I would do is multiply that function by 1/5. So in other words, I'm going to multiply this by 1 over the area. Why would I do that?
To have 1.
Because now the area would equal 1. So the probability of an outcome would be equal to the area, which can now be found through integration. And if you've had statistics, you have z-tables, which were a lot of small iterations where they told you the area from here to here. The problem is integrating this. Now, how many of we're in my Calc 3 class? Okay, we did this integral. I don't expect you to remember the results. We're going to do it again because the results of this integral and 2 similar integrals are the foundation of what's going to be coming next over the next few days. So the question in statistics, and I do this because this is considered one of the single most important calculus results that exist. All of statistics pretty much starts with this. We would like to integrate this. So I'm going to do it as e to the, I'll write it with x's because everybody's way more comfortable doing x's, right? If I put a different letter in there, that just really messes us up, right?
Don't make this square the integral.
Well, I've got this. Let's call, for lack of a better name, let's call this, okay, I for integral. I was going to say a for area. All right. Well, that cannot be integrated. Now, I'm not going to go through the whole process because I do this proof in Calc 3. It's actually a pretty powerful proof, and it's not in any calculus book or any YouTube video that I have ever seen, but I had to do this myself when I was in school because I had to prove something to myself and then I would prove it to my teachers. But it's an absolute generically, I've got a double integral, and the f and the g are functions of x and y, but they are connected through multiplication. If you wrote it as a quotient, it'd be the same thing. They're not a summation. Okay? Oh, one more thing. Region on the xy plane, sorry. So there's 2 conditions here. The region in the xy plane is a rectangle. That's boring. And f and g are functions of one variable at a time. There are xy terms, but they're being multiplied. So I could have a cos x times a y squared. That's okay. Okay, I'm not going to go through the whole proof. I do this in a Calc 3 class, and it's actually quite important that I do this. And this is equal to, and this is a really cool and really important. You cannot break apart a double integral unless 2 things. F and g are connected through multiplication, and my region is a rectangle. Because now it doesn't matter what order I do them, does it? You know you can't just arbitrarily switch that part unless it's a rectangle. So this is a powerful mathematical statement. So if I started with this, I can do this. It's not the answer that I'm really interested in, it's the process, because we're going to use this process a couple of times. There's 2 major integrals that I'm going to prove. I'm going to do one of them today and one of them tomorrow, and then the last one I think we'll do on next Monday. There's a whole bunch of pieces. All of them are located in that same first section. Remember I said last day that first section has more information than is possible to go over? Now, do you agree with that statement?
Yes.
Yeah. So, what if I, just for fun, multiply these together? Oops, sorry. This is kind of boring, but I could do that, right? I just multiplied them together and they both equal the same thing. Yeah, you trying to lose a question? Really
No,
shouldn't
no,
be,
you're
yes.
just doing this for fun. I was about to say how. No, yeah, never mind.
I'm multiplying these together.
Yeah, yeah.
Now, what do you notice? I have constant limits of integration. Yeah, they're infinities, I know, but they're constant. And what else? The x and y's are completely separate. So based on what I just said there, could I write this as a double integral of the product? Would this be legal?
Yeah.
Now, does it matter if I say dy dx or dx dy in this case? They won't make any difference. I'll just say dy dx. Okay. So I just took one impossible problem and I squared it. Okay. Well, you know, we just did something like this recently when we did the Laplace transform, right, with the e. Can I put those together? Yeah. We'll deal with the infinities in a moment. I still can't integrate that, but x squared plus y squared. If this was Calc 3 and you saw an x squared plus y squared, what would you be in a hurry to do here?
Switch the polar.
Go polar? You know, what do they always say? You know, once you go polar, you never go back, or something like that. Could I do this as polar?
Yes.
Yeah. But if I do this as polar, and hold off on that for just a second, this would be e to the what?
E to the negative 1/2 r squared.
But what do I automatically get then? R d r d theta?
Yeah.
That's a one-step integral.
Huh. Now, the tricky part is my limits of integration.
Zero
Okay,
infinities.
here's what I have. I have the xy plane. Do you all agree that my domain is the entire xy plane?
Yeah.
Which of course is an infinite rectangle. Or is it? Wait a minute, if I have the whole xy plane, it's the whole xy plane. Couldn't I think of it as an infinite circle? Because if my circle had infinite radius, wouldn't it still be the whole xy plane? So let's change our thinking from this to this, and it would still be true, wouldn't it? Oh, so that means, what would the radius range from?
0 to infinity.
0 to infinity. Ah, now I'll do my limit.
That's what you said.
So I want the limit, we'll call it t goes to infinity of 0 to 2 pi, 0 to t, e to the negative 1r squared, r dr d theta. Now, if my u is negative 1r squared, then what's my du? Let me write off to the side. If u is negative 1/2 r squared, then the du would be what?
Negative r.
Negative r. Oh my goodness. So you mean all I gotta do is that to make it work? Yeah, and like Mateo said, technically you could consider this a one step. What is it? E to the u du. And what is the antiderivative of e to the u du?
Key to
E to the u. I don't need to change the variable.
But we do have to divide it by 2.
Did I?
and divide by 2.
Yeah, we have to
No.
divide the integral by.
No, we're good.
The chain rule takes care of the 1/2 factor.
The 2 times 1/2 took care of that.
Oh,
Is everybody cool with that? Well, that's all of a sudden not terrible anymore. So this would be negative the limit as t goes to infinity of 0 to 2 pi. Now, what do I have in there? I have e to the negative 1/2 t squared minus e to the 0. Well, what's e to the 0? That's 1. Okay. As t grows without bound, what's that guy doing?
0.
That's going to 0 really fast, isn't it? Do you all agree that that's going to 0? So what am I left with?
Negative 1.
The negative of -1 with constant limits of integration, that's just 2 pi. Wow. Now, what it makes me laugh is I used to use a DiffyQ book, a previous one, where it gave this problem and it gave the result and it says you should know this from basic calculus. I saw this proof in my 3rd year of graduate studies at San Diego State in statistics. Never seen it done in a math class. And if I grabbed 100 PhDs in mathematics, I'd be thrilled if 5 of them knew how to do this. No, most people don't know how to do this. The thing is, this is considered the most important result. Now, so that means the answer to my integral is 2 pi? Not exactly. That's the square of the answer to my integral. So what's the answer to my integral?
The square root of 2 pi.
Now, here's the interesting thing. If you grab any statistics book, this is the definition they use for the normal distribution. It has a square root of 2 pi in the denominator. And everyone should ask the same question. Where the heck did that come from? I just showed you. Now, it's not the result. It's the process that we just did to get that result. It's quite brilliant, whoever figured this out, that, my gosh, if I change it to polar, what's that?
It was Dr. Feynman, the Feynman technique. He did that.
I don't know
The
Dr.
thing,
Feynman.
Richard Feynman?
That was-
Is mathematician or
He sent
statistician?
physicists who created the Feynman diagrams.
but
So you're
that's
saying it
not-
wasn't even a math person that did this? Everybody who does the stats knows this one, but the math people don't have any reason to know this unless you're doing statistics. Now, what if? I'm going to tweak this slightly. New problem altogether. What if I want just the 1/2 x squared? I'm sorry, my bad, not the, sorry. What if I just want the negative of the x squared?
That's just square root of pi.
Well, what changes?
The coefficient.
Let's go all the way to here. If I remove the half,
With you.
then my chain rule factor will have a 2, won't it? Which would mean I'd need a half in front, and then going all the way to the end, this would end up equaling pi, which means that this answer here would be the square root of pi. Now, would that one be hard to come up with once I did this one? No, that tweakage is easy. Now let me do one more tweakage. What if? What's changing?
Now we went from 0 to pi. On the angle.
If that's, if I'm doing dy dx,
Well, we're looking at the normal distribution. We lost half of it.
right, but what if my,
Your radius is going to change.
my radius is still going from 0 to infinity,
but the
but am I going all the way around the circle now?
No.
No, we're in the first quadrant.
You're just doing a quadrant, right?
Am I just doing a quadrant?
Zero to half your
When you
radius.
go 0 to infinity, and then on the y, you should also go to 0 to infinity.
Well, if x is, where are we here? If x is going from 0 to infinity, it's not the first quadrant, it would be the first and
Oh, first and second.
fourth quadrants. I'd be doing the right side.
Oh, right.
So what limits of integration might I use at that point?
Positive pi.
Probably negative pi over 2 to
Negative
positive pi over 2? Everybody with me on that one?
Positive.
But if I use negative pi over 2 to positive pi over 2, this is still a constant times negative 1. Now we're down to
You can multiply it.
pi over 2. I cut it, in other words, I just cut it in half again. But that should make sense to you. Oh, I just did half of it. Instead of negative infinity to infinity like the normal curve, I just did half of it.
Or I guess since it's an even function, right, we could change the limits again to negative infinity to infinity and just multiply by half.
Or the original problem was negative infinity to infinity. Because it's an even function, I have the symmetry and I'm only doing half of it. So whatever answer we got a moment ago, it ought to be half of that one. That is a correct argument. And I just showed you. So there's 3 questions here. The first one I did was the normal distribution from statistics. The second one I removed the 1/2 and we saw where that worked. And then the third one I said instead of negative infinity to infinity, we're going to go 0 to infinity. That feels a lot more like a Laplace, doesn't it? Because that's where this is going to go. Now, I'm going to stop this. We will pick this up again the next thing we do, because I want to refer to these results that we just did today so I don't have to keep deriving them. There's too many, the pieces are not really that small. This is kind of huge, but it's the process that's so cool. Now, the answer turns out to be really, really important, because whatever the answer is, I can now use that. Just like when we derived the Laplace transforms the other day for a couple functions, I don't ever have to rederive them. I just use those results forevermore. Life is so much easier. So now, I want to do things in reverse. So let's start with something simple. I want to do the Laplace transform of e to the kt. What do we know the answer is?
1 over s minus k, given that the restriction is
It's 1 over
s minus k.
s minus k. By
Or
the way,
s is
this is
greater
not
than-
something you should memorize, but you probably want to have those big 4 right in front of you, because you're just going to keep going. We're going to do them so often that I want them to be comfortable. Okay? As long as
S is greater than k.
s is greater than k. Why was that important again? Do you remember?
Because when it goes over,
You all work at the drive-thru, right? Why is that important? One person.
We restricted our domain to be.
Why though?
because otherwise the infinity doesn't go to
Yeah,
zero.
on the other side it would diverge to infinity. Oh, okay, that's why it's so important. If s is greater than k, this converges to this. If s is less or equal to k, it diverges to infinity. That's kind of important. So we always have a restriction like this. So now, what if, let's keep it simple, I have the function, we'll call it capital F of s. I have the function 4 over s plus 2. What is little f of t? What function did I take the Laplace transform of? Meaning, think of it this way. This is the Laplace transform of what function? Is that hard, or do you think that's easy?
Because
Or
you
reveal.
reveal.
Yes, for reveal. Yeah, it's 4e to the negative 2.
You guys like that answer?
Yeah.
So, first of all, let's agree that we like that answer. That was easy. How do I represent that notation-wise? Well, L of this equals f of s, so f of t, we would actually just simply write as inverse function. And the negative one will serve the role of the inverse like it always does. So this would be the notation. The last day I said the analogy would be the Laplace transform, it's mindless. When I take the Laplace transform of a function or a combination, I just do it. It's like derivatives. I don't have to think about it. There's nothing clever, you just take the derivative. But when you integrate it, sometimes you had to do a substitution. Sometimes you had to manipulate. Sometimes you had to, play with things. To say what function's derivative gave me this, is like, here I'm saying what function's Laplace transform gave me this, I need to go backwards. So this would be more on the lines of integration in terms of it's one level higher of complexity, and it won't always be intuitively obvious what the answer is. Okay? So this is the correct notation. So we want to do a whole bunch of problems today so we get comfortable with this, and then we're going to solve a differential equation using Laplace to show how that it's really, really powerful. We're going to take a problem we already know how to do. I don't want it to be complex. We're going to take a problem we already know how to do so you can actually do a quick double check, say, okay, yeah, that's the answer I would have got. Because then there'd be problems that we might not be able to do. So let's start with an easy one. I want to do the inverse Laplace transform of, say, 6 over x squared minus 1. I'm sorry, s squared minus 1. Right, that doesn't look like, if it were s squared plus 1, that'd be okay, right? Where would I see an s squared plus 1? Sines and cosines? That's s squared minus 1.
Yeah.
Shoot, how do we do this one? Well, I'll give you a hint. Go back to Calc 2 for a moment.
Partial fraction decomposition.
If I asked you to integrate this, what would you have done?
Partial fractions.
You would have factored it and then done the partial fractions decomposition. So guess what we're going to do? The same thing. Yeah, I told you partial fractions come up in this course, but not for integration. Partial fractions comes up primarily for Laplace transforms because it'll often be the case that you're gonna have a polynomial all clean and multiplied, but I need it factored. Because, let me go out on a limb here. This is s plus 1, s minus 1.
Yep.
I'd rather take the Laplace transform of these one at a time. It'd be a lot easier. So let's remind ourselves about the partial fractions decomposition. I will assume that everybody's done this, and at one point in your life, you were probably really good at it. But it probably wasn't last semester, right? So, 6 over s squared minus 1, that's the same as 6 over s plus 1, s minus 1, which we'll write as a over s plus 1 plus b over s minus 1. Now, I want to walk you through the process because although everybody's been exposed to this, not everybody is efficient or knows when I can speed up the process. So I'm done with that part. So if I multiply through by the common denominator, here's the first thing that I actually have. True or false?
True.
I just put everything over a common denominator. So do I care about the denominators anymore at this point?
No.
No, when you have two quotients with the same denominators that are equal, then that means you equate the numerators, which means the only thing I really care about now is this. So I want to remind you, could I have gone from here directly to here? Yes.
Yeah.
A lot of folks have a problem with that because they're saying, wait a minute, you can't just get rid of those denominators. What about removable discontinuities and things like that? You'd be right to a point, except that really this is the in-between step, and now I'm equating numerators. So I'd rather just go directly to here because that is the next thing that I'm going to do anyway. Now, there's two ways to do this. There's the traditional textbook way, which everybody learned, and that is to set up a system of equations. So I have AS minus A plus BS plus B equals 1. So AS plus BS, how about if I write that as A plus B times S plus negative A plus B. So that means that A plus B, because there's no S's, equals 0, and negative A plus B equals 1. Would that be correct? And now I'm going to solve that system of equations. And that is absolutely correct. Did I lose?
What'd you say?
Did I lose anything? Oh, thank you. Sorry, 6. Way better. Yeah, no fractions. This is absolutely correct, and this is the textbook approach. The problem with this textbook approach is, what if I have more than 3 factors? What if I had 4 factors? Now you have 4 equations and 4 unknowns, and good luck doing that by hand. You now need a matrix, and remember, we usually do this in Calc 2, so nobody knows how to do a matrix. It's not incorrect. It's extremely inefficient. I'm going to get 2 equations and 2 unknowns no matter what I do in order to solve this. Like, why? I have 2 variables. But why don't I choose the 2 equations? Why do I let the problem do it for me? So what I'm hoping that everybody else learned is if I choose any 2 real numbers for S, any 2 real numbers for S that are different, I will get 2 equations and 2 unknowns that absolutely have to have the same solution. A reminder, this is from remedial algebra. What I just wrote there was 2 equations and 2 unknowns. I could do any linear combination of them and I'd get 2 different equations and 2 unknowns. Those 2 equations and 2 unknowns were basically 2 lines that pass through the solution. There are an infinite number of pairs of equations that would be correct and that they would pass through the same solution. So I demonstrate this in a remedial algebra class. It doesn't matter how I manipulate it. I will always get 2 lines and they will always pass through the solution if there's a solution. I just need to get 2 lines that pass through the solution. But what if I said, let's choose S equal to 1 and S equal to, I don't know, negative 1. Then if I choose S equal to 1, one equation will be 6 equals 2b. Remember, my unknowns are A and B. You can think of those like, horizontal and vertical axes. That would give B equals 3. The next equation I would get would be 6 equals negative 2a, which gives a equals negative 3. This would be akin to having a vertical and a horizontal line that pass through the same solution. No matter what you do, you have to get the solution, which in this case is a equals negative 3 and b equals 3. But doing it this route is always the least amount of algebra. And then if I had 10 denominators like this, it would still be easy. There's no complexity because I'm choosing values that make most of the terms 0.
Why does this work again? I was just.
Any two lines that pass through this, well, you can go back and check them too. Any two lines that pass through the solution will give me the solution. If I take the system of equations I would have gotten by equating coefficients, that's correct. And sometimes you don't have a choice. Sometimes that is the only route. But think of those as being just two diagonal lines. I just made it a vertical and horizontal. Same solution, easier to find. So now going back, this became what? Negative 3.
Plus 1.
So this is the inverse Laplace transform of negative 3 over s plus 1 plus 3 over s minus 1. Do you need to rewrite this as a linear combination, or can you answer it from this point?
You can answer it from this.
It is absolutely correct to rewrite this as a linear combination, but I think because there's no algebra to perform, you can write the final answer as the next thing.
So nothing's stopping you from saying I would let my s equal 0 and s equal 1?
How about s equals 0 and s equals 7? Just for s equals e and s equals pi. I will get the right answer, but it'll probably take more algebra. Any two real numbers you choose will give you two lines that pass through the solution. We just wanted it to be a vertical and horizontal so I didn't have to think about it. So, what is the answer?
Negative 3 sine t.
Sine?
E to the
This
to
will
the
be
negative
E to the negative 2.
plus e to the.
So far, so good? I don't have any disclaimers going backwards. There's no disclaimers on the s going backwards. The disclaimer is only when you do the Laplace transform going forwards. There's no s in my answer, so there's no restriction. Okay, everybody cool with that?
Yes.
Just to clarify, you chose 1 and negative 1 because those will cancel out s.
Because those gave me terms that ended up being 0.
Okay.
So if you guys remember this from way back, what if I had 3 or 4 terms in my product? Now, there's 3 cases as we remember. There are linear factors that are not repeating. There are irreducible quadratics, and there are linear factors that repeat. That's the ugliest one for most of us. That's the one that most people actually didn't learn the correct way of doing it because it's not taught in any calculus book. But it's usually mentioned in the DiffyQ book. So the correct way of doing that one I actually show you in Calc 2. It's not in any of the books. And I'll show you what I mean in a moment. Because otherwise you could end up, I'm going to ask you a simple question that every calc student will end up with a 10 by 10 matrix. But I'd rather get the answer in like 20 seconds. So I'm going to show you how to do things the correct way because the way that's taught is not always the correct way. It's just the way the author learned to teach it, and it's not always efficient. So what do you mean? If I put exponents on these, this becomes nightmarish really quickly.
Yeah.
And you do not learn how to solve that problem efficiently. You learn how to do it by this way. If I put exponents on there, let's say I put a 2 and a 3 on there. Do you realize how many steps would be involved? You'd have 5 equations and 5 unknowns, and doing this won't work because some of them turn out to be 0. So I'm going to show you a better way, but we need to exhaust all the other possibilities first. So what does it mean when we say an irreducible quadratic? So let's go way back to baby algebra. If I give you a 3rd degree polynomial, does it have to pass through the x-axis? 3rd degree, very specifically.
Yes.
Other than a horizontal line, do all lines have to pass through the x-axis? Other than the horizontal line?
Yes.
Yes. So let's go, the line is boring because it's one linear factor. So let's go quadratic or bigger. We know that, right, again, reminding fundamental theorem of algebra, because we are using some of these concepts when we do this, okay? And we usually do this in, I'll do it in descending order, because it's actually nth degree. Okay, this is an nth degree polynomial. let's make the assumption for the moment that the coefficients are real, because they don't have to be real. And if they're not real, that changes all the results. We know as an absolute mathematical statement, this is equal to an times x minus r1, x minus r2, up to x minus what? N. There must be exactly n roots. You can call those the roots or the zeros. There must be. I can have repeats, and I can have complex roots. But if my coefficients are real, complex roots always come in conjugate pairs. If my coefficients are allowed to have imaginaries in them, then they don't come in conjugate pairs. So when you were told that complex numbers always come in pairs, that's not always true. It's true if I'm only dealing with real numbers to begin with, but since we often don't put any restrictions on the coefficients, complexes don't have to. But I have exactly n roots. So what we do is we say, if my roots are complex or have any imaginary part, we're going to back one up. We're not going to solve linear factors that have complex roots. We're only going to solve linear factors that have real roots. So when I have, when one of my terms is x squared plus 4, yes, that factors as x plus 2i, x minus 2i. But that only gave me imaginary roots. So we call this one the quote-unquote irreducible quadratic, because it doesn't have real roots. A cubic has to have at least one real root. A cubic either has one real root, two roots with what? Repeat, or three real roots. Think of that one. Okay? So I'm not interested in the factorization in general, just the rules. So that means that when you're doing this process, every term in your denominator is either a linear factor or it's an irreducible quadratic. Because if it was a cubic, then it automatically has a linear factor. Absolutely automatic. You just only dealt with things that had nice factorizations, right? You didn't have irrational roots typically. Why? Because the factorization would be too difficult. We're going to stick with that. We're going to stick with problems where the factorization is not difficult. Okay, so now I have something. Let me go back to the calculus version. Okay. All right, the integration that I wanted to perform, let's keep it simple, is, 4x squared minus 2x plus 1, and it was x squared plus 1, x minus 3. Okay, I want to do this problem here. Well, this cannot be integrated. Now, there is actually one thing that you have to notice. It's very important. It's subtle. It's minor. The degree of the numerator has to be smaller. You cannot do anything algebraically or calculaically to anything where the degree is not smaller. So if the degree was bigger, I'd have to multiply at the bottom, do the long division, then come back to this. And then what I have as a quotient is of a smaller degree. But the stuff in front would actually be a simple polynomial. So that's not the worst thing. So we're only going to do problems that start off well-behaved. Okay? I cannot integrate this as is, but I can do the partial fractions. Now, I'm not interested in the answer. I'm interested in the process, because that's the part we need the review of. So when I set up my partial fractions decomposition, that's what we just did a moment ago. Is it A and B?
No, it's ax plus b.
Okay. Does everybody agree with that? Why does the last one only need a constant? This is actually a really simple reason. It's not complicated.
Is it because it only has one root that is real?
Well, it's linear. And we said we can't do this unless the degree of the numerator is smaller than the degree of the denominator. But because this is of second degree, the largest the numerator could be technically would be first degree. So I put them both. Is it possible that either A or B ends up being 0? Is that possible? Yes, they both can't be. And it's possible that neither one is. But if I only put the B and there actually was an X term, then I have an impossible situation. It won't work. I won't be able to solve it. So what we did was we accounted for everything it could be. And then I do the same thing I did a moment ago, and I go through the process of choosing things. Okay? So in this case, save ourselves some time and trouble, we'd say ax plus b times x minus 3 plus c times x squared plus 1. Now, there aren't a bunch of real numbers that are going to give me zeros, is there? Oh, darn. What do I do? Well, let's take the obvious one. Is there a gimme up here? 3. Then the left side is 4 times 9, 36, minus 6, 30, plus 1 is 31. And the right side is 0. 10C? Now, again, I'm not interested in the answer, I'm interested in the process. Now, okay, I can pick any two real numbers to finish this out. Well, actually, there's a really good choice.
0.
How about 0? If I choose x equals 0, then what do I have?
Negative 3b
I have negative 3b, x is 0,
plus c.
plus c, but I already have c. Do I now know the value of b?
Yes.
Yeah, so if I throw that over, it'll be negative 31 over 10, so that means that b will be negative, positive 31 over 9. Did I screw that up? No,
Divide by
not
3.
31, sorry, 31 over 30, sorry.
I think we have to set that equation equal to 1.
Did I,
Yeah,
oh,
'cause
oh,
I'm
I'm,
missing one.
no, you are correct, I'm sorry, I'm looking, I see my 0 here. Yeah, Mateo's correct, I saw my 0. Sorry, if I put a 0 in there, that should all equal 1. Okay, let's try that again. 1 equals negative 3b plus 31 over 10. There we go. So if I throw that over, that'll be negative 21 over 10. So this will be b is positive 7 over 10. Okay. Oh boy, what should I now choose for s? Of course, the answer is yes, or x. In fact, any real number.
Just not the two you already picked.
Any real number other than those two. Why? Because I've already got these two values. I'm going to get one equation with one unknown. So this one ends up not being that nasty if I go in this order. That's key. So I took the freebie, used the 0, boom. Okay, it's not always going to be clean, it's not always going to be easy, but that's the process. Okay, we're going to do the same thing in our case here. All right, so. The fact that there are fractions, don't worry about it. I mean, I just made this up. I didn't actually think about the numbers. So let me take one out of the book. Maybe the author was nicer to us. Since I clearly wasn't. All right, how about we do one like, is there something icky in here we can do? Oh, here's a good one. Let's do one that's a combination of things. Okay, how about, I want to do the Laplace transform, or the inverse Laplace transform of 4s minus 8 over s squared plus 4.
So is that 45?
4s minus
Oh,
8
4s.
over s squared plus 4. If it were 45 minus 8, I would have just written
Yeah, it was-
so. Okay. But look at the bottom.
Yeah.
Which ones look like that on the bottom? Which functions of t look like that?
Sine and cosine.
Sine and cosine. So it's probably sine-ish and cos-ish. Do you see a 4? No. What do you see? You see a 2 squared. And that's the thing that's going to show up on my answer. So off to the side. Until we're so good that we can do this in our head, which may or may not occur. If I wanted to do the cosine of 2t, and I wanted to do the sine of 2t, what would those look like? Well, they would both have that denominator, wouldn't they?
Yeah.
I'm just kind of giving you a hint how to be efficient. So, what goes on top in both of these cases?
So the cosine goes
And again,
to S.
have these written down where you can get to them quickly, you know. So this would have
S, right.
an S and this would have a 2. Huh. Well, probably the first thing I should do is pull this apart.
Yep.
Don't try to look at this as one thing. I think we'll mess up if we do that. So can I look at this as, and don't, by the way, don't even factor out the coefficients. Well, I'll factor out the negative. Okay. We'll leave the coefficients because we're not sure where they're going to be needed yet. Okay. Well, what do I need on top? I need an S. I have a 4. Pretty sure I know what to do with that guy.
Yeah.
What are you going to do with the 4?
Pull it up.
Pull it out. It is a linear transformation. The other one, What do I need on top?
A 2.
I need a 2, I have an 8.
2 times 4.
Can I do that? Yes, no, maybe? So can I now write the final answer?
4 cosine theta.
Not bad. Do you agree? That's,
Yeah, the bosses are actually surprisingly pretty chill.
can it get ugly? Yeah, I mean, from an algebra standpoint, anything can get ugly, but it doesn't mean it's hard. It just means it's going to be tedious. You got fractional coefficients, but it's the same thing. So there tends to be an avoidance of that problem just because we get bogged down on the arithmetic and we kind of miss the big picture. That doesn't mean you're not going to see fractions, but it means most problems aren't going to be hateful. But this is a great one. Now, I'm going to give you a calc problem that comes up. This is the one we don't like in calculus. Okay, I'll show you one we do like. I like that one. Heck, I even like that one.
Yeah.
Heck, I don't even mind that one. Why? Because my numerators are ones.
Yeah.
Yeah.
Oops, sorry. I'm using 2, okay. Okay, I'm good with that one.
Ooh.
Right? You know what's coming. Psycho, shower scene. With the knife, right? Always the high-pitched violin. This is a calculus problem that everybody has to do at some point in calculus, and that's about the time you change your major. Because this problem is going to require, well, 10 equations and 10 unknowns. Because the only way I've ever seen to do this in a calculus book is partial fractions decomposition, which is correct. And so what we do, we say, and I'm going to show you the textbook way, and then I'm going to show you the correct way.
You're gonna put 10 equations up there?
So what do? We go a over x minus 2 to the first.
Yeah.
What do we have to have? Every
Every
single possible
Repeated.
10th letter of the alphabet, I believe is J.
Yikes.
Every calculus book ever written says, and you do this. And now when I equate coefficients, great. I have x squared minus 5 equals that, and now I go through, this is a 10 by 10 matrix problem. Boy. By the way, this is how it's always taught. And I really don't like this. I am the laziest person you'll ever meet when it comes to math. So a lot of the processes I show people in my classes, they aren't textbook processes. They're things I figured out sometimes as a kid. They're just because there's an easier way to do this. You want to see the easier way?
Yeah.
If my denominators were x to a power, not x minus 2, but if they were x to a power, would I be challenged by any of the integrations that were to ensue? No, it would be a piece of cake. So why not do something like that? How about if I do something like, let's let, I don't know, t equal x minus 2. Why would I do such a crazy thing? I'm not talking about the integral, I'm talking about the breakdown. Then wouldn't x equal,
T plus 2.
so then x squared minus 5 over x minus 2 to the 10th would be what?
Ooh. Minus 5 over T to the nice.
You guys have seen this before? How many answers am I going to get?
3.
3. How long will they take me to get them?
No.
Beginning to ending, when you get good, this cannot even take you a whole minute.
That's
This is the way you should have learned it. I have never run across anybody who's learned this. But the Diffie-Q books, by the way, most of the Diffie-Q books will show this.
I was just gonna say that is like the use of, but like on steroids.
You gotta like, you understand that this is the formal way. This is not wrong. Just come back next month when you're done. No, what I just did, now what am I gonna do after I break them up?
Just this
I'm gonna
split.
substitute back. But I gotta do this first. So what is this break down to now?
1 over T.
1 over t to the 8th plus 4 over t to the 9th minus 1 over t to the 10th. Now, it's crazy.
This is witchcraft.
So if this were the partial fractions decomposition from calculus, you're now integrating this. And you all told me these were easy integrals. They are. They're just, right, u to the negative. These are all easy integrals. You don't even have to change it. You can write them. Now I've got that. So what about the Laplace transform? Same rules. Same rules. Okay. Now, it's not the final answer that I'm interested in this case. It's actually the breakdown. I want to know that I'm doing the breakdown correctly. Okay, you with me so far on that?
Yeah.
So let's do, grab one out of the textbook. Actually, the author doesn't give a lot of these ones. Oh, here we go. There is a couple. Sorry. I was trying to find a couple of these. Now, I'm going to start low level.
1 plus 1. True.
Sorry, second power, let's start with that one. Where, can this problem still get nasty? If the exponent is large, I still have to expand that. It's a binomial expansion. We know what to do. But if the exponent is large, there's no way around it. You got to expand it. And it means you're going to have a lot of terms. You can't do anything about the fact that you have a certain number of terms. This was going to have 3 terms no matter what you did. Look at which 3 terms were in the answer. So when I did this, it meant that A, B, C, D, E, F, and G were all going to be zeros. But I wouldn't have known that until I did the whole problem. That's why this is a little bit easier.
I don't want to confuse this, but I just want to know, why didn't you include on the first one AX or AX?
Because my factors are linear.
It's 1, right? Okay.
All my factors are linear, so this is still a linear factor. It's not an irreducible quadratic. It's still just x minus 2. Now, even if it was x squared minus 2, I would factor that further. So that's not really the thing. But all of these get constants because all the factors are linear. The fact that they're repeated just means I got to write all of these terms.
So if the denominator was x squared minus 2, you would put AX.
Well, then I would factor x squared minus 2 because it's a minus. It would actually have to be x squared plus 2 before I would leave it as an x squared. Right? A sum of squares would be the kind you typically leave. Now, what should I do here? What do you think? Anybody?
Well,
I definitely don't want to make the bottom complicated.
yeah.
Multiply the top out. Yeah, this one actually is pretty nice. So what's the top going to multiply to?
S squared plus 6s plus 9.
And now what we're going to do, make that into 3 quotients. S squared over s to the 6th plus 6 over s to the 3rd plus,
Wouldn't it be
sorry,
s to
s to the,
fifth?
I can't understand, s to the,
Because
oh,
it's
there we go, I'm sorry, 5th, and then what's the last one?
S to the 9 over.
S to the 6th. Okay.
So can we always compare essentially the degrees of both the top and the bottom to see what we will expect out of the partial sums that we get?
I'm not
So that's what.
sure I understand.
Yeah, it's already.
The answer is probably yes, but you have to translate for me. Well, my bottom was something to a power.
Right.
Why was that a nightmare? Because it was not something to a power, it was x minus 2 to a power.
Right.
When I did my substitution, I made it t to a power. So isn't the problem we just did over there pretty much the same as the problem I'm asking you here in terms of the form? Yeah, so I don't need to do anything here.
Yeah.
I just expand this one. So that's what I want to do. If the denominator were s, plus 5 to the 6th, that would be more challenging. Okay, that is a problem we will be able to handle. I don't need to do it yet.
No.
Okay? Now, what do I do with these guys? Well, let's see.
Is that just one?
This is one we did not prove this. I said this was one you get to use. For n, an element of the positive integers, what is this?
N factorial over S3 minus 1 or plus 1? Either of the two.
Anybody know?
N factorial.
Oh, it's a
It would
quotient.
be n factorial over s
N
to the n
factorial
plus
on
1.
top and on bottom, s to the
N plus 1.
n plus 1. Good.
Okay, that's it.
And again, have those located nearby. There's on page, if you have your book, well, actually, they're located in two places. On page 282 or the entire back of the book. But there's too many on the back of the book. You don't, there's so much information you don't need it, right? You just need the big four, because those are the ones you're going to use over and over again. Well, if this is true, then I'm going to need to do something to each of these. I cannot do any of those yet.
You need coefficient.
I need coefficients. Okay. So that means working, I don't need to rewrite it. I just need to work backwards. So whatever my exponent is here, I need the appropriate factorial. So what factorial do I need on top here?
3.
So let's go like this. That's it. That's all I need to do to make this one work. How about the next one?
4 factorial.
And then the last one?
5.
Now, so what do I do with the other numbers?
They would also be pulled out.
Negative factorial.
I pull them out, so in other words, I'm going to pull those out as coefficients of my answer. So I'm going to rewrite this first before I give the answer, because I don't want anyone to get lost here. Legal move, correct?
Yeah.
So how about if I rewrite the first one as what? 1 over 3 factorial. I'm not going to even bother evaluating it yet, because I don't want you to lose where it came from. Okay, have I changed anything, or did I translate it correctly?
Yeah.
That looks right.
Is good.
Yeah, that's good.
Don't think we have any booze. That's French error. The boo.
Huh. I would say oopsie.
Start with that one. What is this then?
T cubed.
That's t cubed.
T to the full 8. That's T to the 5th.
Okay. I would go ahead and simplify these. You have a calculator, so what's this one?
1
1
over
over
6.
6. 1 over 24.
1 over 2 factorial, so 1 half. That's 3 factorial.
That'd be
over
24.
4
So
factorial.
4.
Oh, yeah.
9 over 120, so 3 over 40. We'll do some if we can. Think of it in reverse. If I had asked for the Laplace transform of this, you would have told me the answer was this. You wouldn't have needed to factor it. You would probably have it spread out. If it factors, that's nice. Do I need to factor it in reverse? Probably not. I don't know that there's any advantage. It wouldn't be incorrect, but I just don't think that's a thing you would do. The one that's going to give you the most trouble, I'll guarantee, is this one. Because of the coefficients, you will usually always have to introduce a factorial coefficient. It's probably not going to be as part problem. Yeah.
Why did you choose 3 factorial? Can you choose a different time?
Well,
Like, can you start at 4 factorial and go up to 5 and 6?
well, the problem is, look, this is an s to the 4. That means it needs a 3 factorial on top for me to go backwards. So if it's s to the 3 plus 1, then it needs a 3 factorial. So going this way, that's what I get. So that means I have to do the inverse Laplace transform of something that looks exactly like that
Oh, okay.
in order to get one clean term in reverse. Everybody okay with that? Okay, not totally weird. So this is the next thing. This is algebra. This like what you said. It's you say clean, or what was the term used? You said this stuff is pretty,
Oh, it's chill.
it's chill. That's even way better. It's way better than the answers are clean. Okay. Yeah, the problems can get ugly. Don't dwell on the ugly. All right, now we're going to do a very specific, I guess I'll use this part. We would like to, hopefully I can get through the problem. I lost a couple minutes at the beginning of class. Let's see, which one do I want to do? I want to do, hold the phone. Did I write it down? Oh, there we go, there we go. Let's suppose the following. Okay, make sure your F's don't look the same. Here's what we want to find.
Oh. Let me guess.
Well, in the first case, we know this absolutely is true. Agreed?
Yeah. Is it F of
The Laplace transform of this is where I get my f of s.
plus
Okay?
Laplace transform?
So that's not the problem I want to do. So when I put an exponential in there, or like on your quiz, I'm going to put a t in there. In class, we did a cosine in there. We had to do a parts. We had to do some stuff. It was kind of yucky. So I want to do the Laplace transform of f prime of t.
Is that not just?
F
So-
of 0.
What's going to happen? I want to do that problem.
Yeah.
Well, now think about this logically. This is an integration by parts. But like the gamma function the other day, we did an integration by parts that produced a recursive definition. We got the original problem back. So if I do an integration by parts, do I want this to be my u or my dv right here?
Your U. Oh, your DV.
I want it to be my dv, so its integral is back to f of t, and that's what's going back in the next integral. Everybody see that? So that's going to determine this. You're going to like this because it's actually really simple.
Why are there two DTs again?
Oh, I don't know.
Oh.
You're standing too close to the board. Just in case you know,
Super.
didn't have enough. It's a super integral. All right, so we're going to let u equal e to the negative st, then dv is f prime of t dt. Then my du is negative s e to the negative st dt, and my v is f of t. Now, I don't want to attack the improper integral first. It's too messy doing limits of. So let's do this problem first, shall we? And then we'll come back with the limit part. Let's just do this. So uv, so the e to the negative st f of t minus the integral of v du, so it'll be a plus. I'm going to put the s on the outside, or actually, no limits yet, sorry. And then I'd have what? E to the negative st f of t dt. Okay? Everybody okay with that? So now, I guess I probably should have done that on a sideboard. This is now equal to the limit as, we'll say c goes to infinity of e to the negative st f of t plus s times the integral, and I'm not going to take the limit. I'm just going to write the improper integral. Why would I do such a thing?
Because it's a Laplace transform.
Because isn't that f of s?
Yes.
Ooh. So I have an s times an fs in my answer.
Where did the C come from?
Because it's an improper integral.
Okay. Oh, we
So-
just called it a random letter.
It's something of this, not an s or a t or a
Okay.
Is that S or 5? The one.
There are no fives in the problem. These are always s's. Come on, guys.
Oh,
This is the definition of the Laplace transform. I know my fives are bad, but I try to get a little bit of straights. Okay. This is the part that's going to be a little bit tricky. Okay, if we evaluate this at 0, then I have e to the 0, which is 1, f of 0, which is f of 0. It's just a number. Doesn't necessarily have to be anything particular.
Evaluating an infinity is just zero.
We set the function.
Remember, this is in the bottom. Now, you say, well, do I have to use L'Hopital's rule? Actually, it's easier than that. This was bound, it's of exponential order. That means that it's beneath, it's way smaller than the exponential, and the exponential is approaching zero rapidly, so what can we say about the whole thing?
It goes to zero.
At the C, it's going to zero very fast, so all that's left is the minus
F of zero.
this. So the answer to this is S, f of S minus little f of zero. This is a formula. I'm going to write this one down. You're not going to re-derive it. Now, have we solved a lot of third, fourth, fifth, sixth order differential equations in general? No, but we have solved a lot of second order. So we need to do this one more time. We need the Laplace transform of a second derivative also. And that's the only ones you're ever going to need. There's actually a recursion that shows you how to do it for the nth derivative. Don't worry about it. You're never going to do that. Seriously. It's, yeah, it's there. It's just not necessary. So let's do the same process. But now I want to do the Laplace transform of, that was f prime of t. So now we want to do it of f double prime of t. So again, this is going to be 0 to infinity e to the negative st f double prime of t dt. But just like we did on this one, don't I just need to get something that looks like this? Because this equals this,
S, F of
right? So I don't need to get it all the way down to here. I just need to make that one look like this one, and then I can use this result. Everybody okay with that? So we'll do the same thing. We'll start with the general antiderivative. Okay. So if we let, again, our u be the exponential and dv be the second derivative, then the du is negative s e to the negative st dt, and v is the first derivative. This is part of the bounding things so that I can make sure that they're not going to grow out of hand, by the way. So what does this become? uv. So it's e to the negative st f prime of t minus, so plus s times, well actually, sorry, let me write the integral first. Plus s times the integral of e to the negative st f prime of t dt. Okay? So now when I go back to here, and I said, okay, now I want my limits of integration. This will now be, we'll do like we did a moment ago. The limit as, call it c goes to infinity of the first part, e to the negative st f prime of t from 0 to c, plus s times the integral from 0 to infinity e to the negative st f prime of t dt. Well, just like before, when I evaluated at c, that's just a constant, and then that term's going to 0 very rapidly, right? Or at least it's going to 0 faster than that guy's going, but that's probably a better way of saying it. Minus what? F prime of 0. That's what that's going to end up being, just minus f prime of 0. What about this? Well, this part here we just showed was equal to this. So that means my whole answer here, I'll bring it down here, ends up being s squared times that. So s squared, capital F of s, minus s times little f of 0, minus f prime of 0. Oy vey. But now we have the Laplace transform of the first and second derivative. You don't actually need to rederive it. You just need to start at the beginning, plug and chug.
Can you explain why it's minus f of 0 and minus f prime of 0 in both of these cases? I remember you said that it
Oh,
was
because when I evaluate this, what's this? I'm just saving myself a little time. This is e to the negative sc f of c minus 1 times f of 0.
Oh, I see what you mean. Okay, okay.
And that term's going to 0, so that's all that's left.
Yeah, that makes sense. And it's the same case for the prime.
Because remember, you're replacing this with C and you're replacing it with 0. So it's the same. So I get this. I had noise. Oh, here we go. I'm not sure we have time to finish one, but I'd like to start a differential equations problem. All right, let's do. And let's see, what letters? I think the author's using X and Y. Oh, they're doing T, sorry. She's doing T. All right. dt squared, how about minus 3 dy dt minus 18y equals 4 e to the t. I want to solve this, but I want to do it using a Laplace transform. Now, understand then that y equals, right? Y right now is a function of t. So the Laplace transform of y will be my capital F of s.
Yeah.
So in other words, y is my little f of t. Everybody see that? Y is a function of t.
Yes.
So think of y like your little f of t. So the Laplace transform of y equals f of s. Because you don't usually use function notation when you're writing a differential equation like this. So I'm going to do the Laplace transform of all of this. Well, I'm pretty sure the right side is going to be easy. Now, in all likelihood, you'll have initial conditions. Okay? I'm not worried. I don't even care about the initial conditions. I just want to get you set up. Okay? So when I do the left side, what am I going to get? Well, I have it right over there. I'm going to get s squared f of s minus s times what? Little f of 0. This is where initial conditions would come in. You'd be told f of 0 is this, little f, f prime of 0 is this. And we'll do something like that in a moment. Minus f prime of 0, that's that. Minus 3 times, now go to the far one, s f of s minus little f of 0. Then what? Minus 18 times just capital F of s. And all of this is equal to the Laplace transform of that guy, which is
4s minus 1.
s minus 1. Now, let's suppose, I'm just going to make life easy. Let's suppose that f of 0 equals f prime of 0. I'm going to be really late. Okay, everything's 0. Yeah, you're usually not going to get this lucky. Let's just, we want to get. So, why is that cool? Wow. Okay. Now, what I need to do is gather the f of s terms and then put everything else on the other side. So I have an s squared minus 3. Is that right?
Wow.
Yeah.
Am I missing anything?
Minus 3s.
Minus 3s, yeah.
Or sorry, minus 3s.
Minus 18. All times f of s. Equals.
Yes? We got lucky. Does this factor? It's not always the case. This doesn't always factor.
Yeah, no.
So therefore, what does f of s equal?
4 over s minus 1 times s minus 6 times s plus 3.
Everybody cool with that?
Yep.
I now want to simply find the inverse Laplace transform of that. But in order to do that, I need to do a partial fractions breakdown on that kind of thing. Will that be hard? Well, if we do it the way we did it earlier by choosing values of s, it'll actually be very simple because it's 3 distinct linear factors. 0 repeated factors, no irreducible quadratics. That's actually our favorite kind of problem if we know the trick I showed you earlier. I've taught many classes over the years where people never saw that. In fact, a number of years ago I was taking a graduate probability class, I think it was, at State. I used to just every now and then go back and take a class that just sheer boredom. And the instructor had been there for 30 years, and he's teaching a problem with things called moment generating functions, and there's some pretty gnarly algebra. And he got to one of these, and we've got a half hour left in the class, and we spent the next half hour. He couldn't get through the partial fractions breakdown, so he said, okay, I'm going to leave this to you guys to figure out at home. And I had done the entire thing from beginning to end in like 30 seconds. And so after class, I said, can I talk to you? I said, why didn't you just do it this way? But he went, he goes, oh, did you come up with that? And I go, no, I can't take credit for that. I go, this is kind of what I teach my own. So he goes, that is awesome. I've never seen that. This guy was probably 70 years old, PhD in mathematics, been doing this whole life. He'd never seen what you guys are doing. And so he spent a half an hour doing something of this nature and couldn't get it. He kept screwing up the algebra. And then when I showed him, I go, we could have been done in under a minute. We could have, so the next class we went like triple speed because we got way behind it. But I just thought it was interesting. Somebody who's a mathematician, he had no idea there was an easier way. This is unfortunate. All right, so here's what we want to do. Again, it's not what the answer is, it's the process. So we're going to go A over S minus 1 plus B over S minus 6. We might actually be able to finish this, by the way. So if I put this all over one common denominator and then equate coefficients, the next thing I would have is this. This is not some hard and fast rule. This is just the way I think most people, I'd say over all the years, I'd say at least 3/4 of the students. How many, what we're doing now where we're going to plug in S's, how many learned it that way? How many learned it by setting up a system of equations and solving it the long way? Yeah, you had an instructor who didn't love you. Yeah. See, I love you. That's why I show you the easy way. I want you to, I need you to be done with all of your work before 7 p.m. tonight. Because you know what's happening after 7. You got the Lakers on one station, and you got the Kings on another, and if you're like me, you're going to be going back and forth for the next 2.5 to 3 hours, and you can't be doing math while you're trying to concentrate, Yes. I can always tell when someone scored a goal because you'll have like a mess up on your paper kind of thing. So what values of S should I probably choose?
6,
1, 6, and I don't know, how about -3? Okay, and in each case it's going to be 4 equals, agreed?
Yep.
Okay, when I choose 1, 0, 0, 1 minus 6 times, so that's -20A? Is that right?
Yep.
So A is -1/5. All right, I'm going to choose 6. So 0, 0, 5 times 9. Is that right? So 45B. Oops. So B equals 4 over 45. And finally, I'm going to choose -3. So 0, 0. So -4, -9. So positive 36.
Yeah.
That's the implication symbol, in case you're wondering. 4 over 36, or 1/9. That means then y, which is the inverse Laplace of f of s, that's going to be the inverse Laplace of, now I would put the fractions in front, okay? I wouldn't put them on top. So how about 1/5 times a over s minus 1?
Oh.
Are they all positive?
Wouldn't A be the one?
Oh, I can't see. A is -1/5, sorry. That's what I'm asking you guys. Is that right?
On the right, you would just write it as like 1 over s minus 1 instead of a.
Oh, I'm sorry, thank you, yes. Sorry. That is our A, absolutely. And then what's the next one?
It's 4 over 45.
It's two-sided, it's 4 over 45. You guys are gonna make me squat down and look over there.
S minus 6.
S minus 6. You don't realize that I have no peripheral when I'm standing. That's why I always step way back there. And what's the last one? Are they all positive?
1/9.
Except for that one.
Yeah.
Plus 1/9, and then it was 1 over.
S plus 3.
Can you give me the answer now? Without doing anything else?
Yes. negative 1/5 e to the negative,
to the t.
plus e
Or
to the t. Quarter over 45 e to the 60 plus 190 to the negative 3t.
Three to the. Did you know how to solve this problem,
Yes,
old school?
yes.
What was your auxiliary equation? And its roots were what?
Oh, yikes. 6
M minus 6, M plus 3, so your roots were 6 and negative 3.
e to, oh.
And you would have then used method of undetermined coefficients for the e to the t.
For the particular.
So does the answer look like what it's supposed to look like, more or less?
Yes.
Yeah. That's a good thing, by the way. So we did not do any calculus whatsoever on this problem. In a sense, well, once we had the transformation for the first and second derivatives, we just plug and chug. Now, I picked these guys to be 0. That wasn't necessarily the most practical choice. I just wanted to get them out of the problem. I probably would have been more judicious in my choice to give us happier coefficients. That's kind of cool, huh? So that's just an application of using the inverse Laplace transform. It's certainly not the only one. It's not necessarily the most important one. Okay. Go ahead. You go ahead and stop that. I think.